start recording. Alright, and minimize the OBS. Alright, so last thing we were talking about was energy. In particular, we have kinetic energy translation, which is 1/2 mv squared. We have kinetic energy rotation equal to 1/2 I omega squared, and V and omega are related to each other such that V is equal to R omega. And we have some potential energies. We have potential energy of gravity, mgh. We have potential energy of a spring, 1/2 mv squared. Not mv squared, good heavens. Kx squared. There we go. There are torsion springs, so you could in principle have a k and a theta square here. So that k would have a different value for a spring constant. And we have what else we got? Potential energies. I think those are the good ones that we're really interested in, and those are the kinetic energies that we care about mostly. And then so what we and then we also have work, which is equal to some force times the displacement. This is most useful for cases where we have a work of friction. And so you end up with the force of friction times our displacement. And so that'll be mg and probably let's get everything in there properly. Force of friction itself would be mu k normal times displacement. Normal force is more often than not mu k mg cosine theta, and then we have our distance. And so we'll rearrange this a little bit, turn it into mu k mg d cos theta. Let's see here. What was the last problem I talked about? I don't quite recall. I believe it was a ramp problem of some flavor, wasn't it? I think it was. Yeah, it was a ramp problem. And I think it was just the object coming down the ramp, no other forces. So let's rehash that problem. There's a box. Oh yeah, I remember the problem. Dang it. I had basically weaseled myself backwards into the energy conservation is what it was with the MGH here. And so let's see here. So energy conservation, as far as I'm concerned, energy initial is equal to energy final plus any work others that might happen. They'll either be friction or they'll be specified as work other equals so many odd joules. And so this is energy conservation. Which works best when the work other is 0, of course. And so we break this out. If you were to go to A+ tutoring in College Station, Texas, what they like to do, they like to list out all the contributions. They like to say kinetic energy trans initial plus kinetic energy rotational initial plus potential energy of gravity initial plus potential energy of a spring initial is equal to kinetic energy trans right here, trans final, good heavens, plus kinetic energy rotational final plus potential energy of gravity final plus potential energy of the spring final plus work other. And so then they have their students go and they listen them all out, and then they can have their students get in the habit of writing them all out so they don't forget any. And then if any of them are 0, they just cross them out as they don't need them. I mean, it works. I don't complain a whole lot, but you know, the way I like I like writing down the things I actually need rather than getting rid of things I don't. But that's a personal style preference. And so, good heavens, try that triangle again. So we got triangle. Let's make a straight line. Close enough. Some angle here, we'll call it 36.9 degrees because that's our 3-4-5 triangle. Right angle goes there. Some box goes up here. We'll give our height, say 10 meters. You don't need the mass, and then everything comes down to the bottom. So we have, well, what we got initially. Well, the only thing we got initial, well, we got to specify that my velocity initial is 0 meters per second. And I would like to know V final and acceleration. Okay. So my initial energies, I'll go through my list here. The only thing I got is my potential energy of gravity. And that is equal to, and come along this whole long line here at the bottom. Well, the only thing I got is my translational kinetic energy. And so I got kinetic energy, translational. All right. And so now we have mgh on the left is equal to 1/2 mv squared on the right. Divide everything by m goes away. Multiply by 2 gh, and take the root. Is equal to my velocity. And so we get that velocity is equal to 2gh square root of 2. Gravity is 9.8 meters per second squared. And we're up 10 meters. Therefore my velocity is square root of 2 times 9.8 times 10 is 14 even. 14 meters per second. All right. So there's my V final. How do you get my acceleration? Well, how far down did it come? I came down this way, 10 meters, but I have a 36.9 degree angle here, so that means that this is a, oh no, I screwed up. That's 3, that's 4, and that's 5. Oh, shoot. Oh well. Well, the distance I traveled then. Now, this guy, that's in a 3 to 5 ratio. Back up just a little bit. 3 to 5 is equal to 10 to some distance traveled. So that means that distance is equal to 5/3 times 10. All right. Yeah. So I have caused a slight problem for myself. Anyways, well, get past that. 5 times 10 divided by 3. And so distance traveled is 16 2/3 meters. So now I can work backwards and find my acceleration. So v squared is equal to v naught squared plus 2ad. D is known. V final is known. That's known. This is the only guy we're missing. And this is 0. So divide that by 2d. So v squared divided by 2d is equal to my acceleration is equal to 14 meters per second squared divided by 2. Distances of 16.7 meters. And then it comes out to be 14 squared divided by 2 anes. 5.88 meters per second squared. Now, obviously, we can look at this from the direction of forces. I got a box like so. We have gravity pulling down this way, force of gravity. We have a force of gravity perpendicular going that way, and force of gravity parallel over here. Well, we don't care about this guy here, we just care about this one over here. So that's force of gravity sine of the angle. So that turns out that means that force of gravity parallel is equal to mg sine theta, and that is equal to ma. M's cancel, therefore a is equal to g sine theta. So that's 9.8 meters per second squared. Theta sine is opposite. So that is a 3 over 5. And so 9.8 times 3 over 5. Yep. 5.88 meters per second. So, what I've found, one moment. I found that, personally, there's the personal style that I like. My personal style is that I like to use energy conservation to find my velocity. Find my velocity with energy conservation. And then use this kinematic equation here to get my acceleration. That's the way I like to do it. I have found in years gone by that students like to do what they know. They like to they've exercised forces because they, for physics 201 and 231 students, they've been exercising forces for like 3 weeks, and so they're really good at forces. They know them really well, and so what they like to do is exercise what they know. And so they use their forces to figure out what the acceleration is, and then use the same kinetic equation to find out what the final velocity is. I don't particularly care how you go about it, just so long as it involves physics and you get the correct answer. And then you follow the, the good. They follow the good, follow good practice with your forces or your energies, and that you do the math right, and then you get the, and then if you do the physics right and the math right, then you should get the correct answer. It'd be a rare day if you don't get the correct answer. I'm not going to be particular about how you go about your answers, so long as they are correct, unless I specifically specify particular steps. Make sense there? Questions? Alright. Let's make it fancy. No, make it fancier. Let's change out the height for something that actually makes good sense here. Let's go for, let's make 9 meters. That should work a little bit better. All right. Let us let's add friction in. Friction, connect friction equals the list number I can't exceed. Arctan of 36.9, 4/5. Nope, hold on. Yeah, 4/5. Nope, 3/4. Okay. Alright. Let's make our friction a half. That would work. We gotta go somewhere with that. Alright. Energy initial equal energy final. Oh, wait. That's not where work other goes. I'm so sorry about that. Work other is initial state. My bad. Work other is part of the initial part. So the reason why work other is part of the initial stuff is that the way that we imagine work other to be in general is it tends to be, we think of it as a source of energy. We think of, say, a force pushing on the object, whatever it is. And given that we do that, then it turns out it belongs up there as a plus initial energy. Personally, I don't like that so much. Personally, I like to, I don't have a particular problem with work other being a plus initial up here. The thing is that most work others tends to be friction. And so friction pulls away. It's a sink of energy. And so it's actually minus work other as a final state. And so this minus sign here will actually take the minus sign from this here. There's that cosine, yeah. There's a cosine, not there. There's a cosine between force of the angle between force of friction and the displacement. And this is 180 degrees. And so there's actually a minus sign that shows up right here. And so if I'm subtracting a negative thing, then I get a plus friction, a plus work of friction, a plus value for my work of friction in my final state. So if we work out this way, then we have a potential energy from gravity equal kinetic energy, final, translational, and then we subtract off the work of friction. So now I have mgh is equal to this guy here, 1/2 mv squared minus this guy right here. So that's minus and negative. Minus negative was plus. Plus mu k mg d cosine theta. Yeah. So, divide all the m's out. Subtract this guy back to the other side where he came from. Oops. So we get GH minus mu k G D cos theta equal 1/2 v squared. Square, I say. Whatever. Try again. There we go. Squared. Multiply both sides by 2 and take the root. So we get 2 GH minus mu k GD cos theta equal VF. So now I can punch in our numbers. Square root 2. I'm going to pull the 9.8 out of both of those. H is 9 meters minus mu k is 1/2, 0.5. G's are pulled out. D, well, what's D? This is how far we traveled down this way. So that'll be, let's see here. Let's see if I can do this right better this time. So let's do H over D is equal to 3/5. So now I need the D, so then that means that D is equal to 5/3 times 9 meters. Oh, that's better. 9/3 is 3 times 5 is 15. So our distance traveled is 15 meters. And then we got this cosine of the angle. Cosine is the adjacent of the hypotenuse, so that's 4/5. Calculator, I need to know this value. Square root of 2 times, I said times, 9.8 times, again, 9 minus 1/2 times 15 times 4/5, and execute. I get 7.67 meters per second. Like so. Questions? Makes sense? Not hearing any. Dang it. Time is that? Oh dear. I have, so we no longer require any of these. Of course, my mouse doesn't work. Why would it? Alright. Delete all that. Alright. So, let's have one more problem here. Which I want to go with. Let's go with the one that I can't screw up just yet. There got two, but I can do both of them. So we have a pulley. Dang it. Got a pulley. Two masses hanging off of them. Like so. M1, M2, MP. Alright, and I would like to know, say M2 descends some distance. Alright. Dang it. So, wanna go that way? No, let's go that way. Let's start with M2 on the ground. On the ground? Let's start a little above. Let's start a little above the ground. Put an H here. There we go. And then this guy will descend some distance D. Alright. So, what energy do you have? An energy initial equal an energy final. V initial is equal to 0 meters per second. So, then energy initial, well, that's mg1. Let's actually specify more things. One more. We'll say pulley is, we'll make it 1/10 of a kilo. M1 is going to descend H, so let's make it heavier. We'll make it 2 kilos. And M2, we'll make it a 1/2 kilo. So, what energy we start with? We start with the potential energy for 1, the potential energy for 2, and that turns into M1 is going to hit the ground, but M2 is going to end up in the air somewhere, so that's going to be potential energy 2. And then we have kinetic energy for 1, the kinetic energy for 2, and the kinetic energy for that pulley. This is everything we started out with. So now we can do potential energy M1 GH. This H is going to be distance D. It's going to follow the distance D. M2 GH from starting position, and that'll be equal to M2 G, and then this guy's going to go up D in addition to his to the H already has. D plus H. I need to specify those here soon enough. Right? Not right. Well, we need to specify D. H we don't need to specify. We'll come back to that though. Plus 1/2 m1 v squared plus 1/2 m2 v squared plus 1/2 I omega square. So with that singular block on a plane that we had in the previous problem, every term had the same m in it, and so we could divide out the m on it, so it didn't need to be specified. In this case, all MS's are different, and I cannot divide out the m. I have seen many students divide out not equal m's and expect to have the correct answer. It will not be the last time nor the first if you do it yourself, but I'm warning you now, so you might have the chance of not doing it again for the first time for me. D, let's make it 3/4 meter. H, why do I not need that guy? Well, subtract this m2 gh to the other side. m2 gh. Well, that's just going to cancel this guy here and leave me with D. Okay. So now I have m1 gd. Obviously, I need my v final. That's what I'm looking for. M1 gd. So that's where all my potential energy is going to come from. This guy here, and I need to turn it into m2 gd. I can take these two and add them together, so I'll do that immediately. 1/2 m1 plus m2 v squared plus this guy here, 1/2 I omega squared. Alright, so we're going to say this guy here is a disk. So that means that I need to specify his radius here soon enough, right? No, I won't. No, I don't. 1/2 mp r squared. And that omega, this guy here, well, we can fiddle with this a little bit and get rid of the omega. So that means that omega is equal to v on r is my omega. Okay. So that means that 1/2 mp r squared, and then this guy, v on r, v over r squared. R squares cancel. R is now irrelevant. So now this kinetic energy rotational is equal to 1/4 mpv squared, which I can add to this term here, and so I will. So that'll be m1 gd is equal to m2 gd plus 1/2 m1 plus m2 plus 1/2 mp v squared. Alright, and this is the guy I'm looking for right here, all by himself. Okay. So subtract this over to the other side. m1 minus m2. Try that again. m1 minus m2 gd. Multiply this side, left side, by 2. We get m1 plus m2 plus 1/2 mp v squared. Divide that over and take the root. V is equal to the square root of a lot of stuff. 2 m1 minus m2 gd divided by m1 plus m2 plus 1/2 mp. Alright, plug in our numbers. 2 m1 is 2 kilos minus m2, which is 1/2 kilo, times g, 9.8 meter per second squared. D, distance, is 3/4 meter, 0.75 meters, divided by 2 kilos plus 1/2 kilo plus 1/2 of a tenth, 0.1 kilo. Answer. Square root of 2 times 2 minus 1/2 times 9.8 times 0.75 divided by begin. 2 plus 1/2 plus 1/2 times 0.1 and execute. 2.94 meters per second. All right. Questions? Make sense? Hearing none. Yeah, this worked out perfectly. All right. So, one of the things I like to do is I like to predict where things are going to land. So, I like to predict things. Theory is great and all, but if it's not carried out in practice, what's the point of the theory? So, last semester, I 3D printed this ramp here, and also this ramp here. They have if I can just stay next to each other, the same height. Right? And so that implies that when they come down to the end of their ramps here, they'll have the same kinetic energy. So the question is, where do these things land? How far away do they get? On Friday, we'll find out if I have any predictive powers. So we have a ramp. With some height, h, and we got marble, start at the top, and then roll down to the bottom, and it comes off here. And then it'll roll off the top from a table from its own height. We'll make this capital H. And then it'll hit the fall down. And I want to know this distance here. Okay, so first thing I need to know is how fast am I coming off this guy here with. So, I have a potential energy, initial, and that is equal to kinetic energy translating plus the kinetic energy of my marble rotating. So that'll be mgh goes here equals 1/2 mv squared plus 1/2 I omega squared. All right. So I is that of a ball bearing solid sphere. So I have acquired some ball bearings, and so now let me guess. Ford does not have it on his exam, does he? No, of course not. Why would he? Oops, don't do that. Bring that back. Come back over here to the meeting. It is close enough. Mathematica, come forth. In an older exam version, I have it in the files at the bottom. And of course, it wants to stop and evaluate everything. Solid sphere. That looks like a 2/5 to me. Oh, come on. Make it bigger. Yeah. 2/5. So I is equal to 2/5 mr squared. Okay. Now, omega is equal to V on R. There's a problem with this thought. It's not just R. Let me show you. When we say that omega is V on capital R, being the radius of the sphere, we assume that we're actually rolling down a flat surface on the bottom of the ball itself. Come here. But we're actually putting the marble in this trough. Oops. So that actually falls down a given path. Like so, right? We'll get those back later. So we're not rolling down a surface like this. We're rolling down a surface like that. And so if you work out your geometry off of this, we're actually rolling here on these edges and not down the middle here. So it actually turns out that this is equal to R square root of 2 on V. Capital R. And now we can actually put things in. So that's mgh equal to 1/2 mv square plus 1/2 I 2/5 mr squared, and then put this guy in, and we get v over r root 2 squared. This r squared cancels with that r squared. And then this guy here, this root 2 gets squared, and so he cancels with this half here, that 2 there. And so we get mgh is equal to 1/2 mv squared plus 1/10 mv squared. Now all these m's refer to the same m because it's the same marble that's rolling. So divide out all the m's. So you have GH is equal to a half plus a tenth. So it's 0.5 plus 0.1, so that's 0.6, or also known as 3/5. 3/5 m, no m. 3/5 v squared. So v coming off the top here, v is equal to the square root of 5/3 GH. All right. So now the ball goes into ballistic motion until it hits the ground. So how long until it hits the ground? Well, that's capital H is equal to 1/2 GT squared. Solve for t, and we find that t is equal to the square root of 2h on capital G. And then our distance traveled going this way, that distance here is equal to VT. Okay, so that means that this guy times that guy. So our distance is equal to the square root of 2h on G times the square root of 5/3 G little h. Okay. Well, we can put things that are under the root, two things that are under roots together. So it becomes square root of 2 capital H over G, 5/3 little g h. Those guys cancel. And so this turns into the square root of 10/3 times capital H times little h. And the question is, what values are these? That we will save for Friday. On Friday, we will take this ramp here and this ramp here. We will measure their heights, see how far they come down, and then we will measure our table that we're launching off of, and we'll make a prediction for how far they will go with actual values. So, to be determined on Friday. So these are some energy questions that we're going to that are related to I could be asking you about. I don't think I want to test a little bit further on those right now. So on Friday, I think we'll have a little more discussion about these here. We'll see if I'll ask some of you to show us how these are done. I suspect I might get a little more participation on Friday than I do online. And we'll see where we go from there. Yeah, I think that's about it. So, any questions? Hearing none, I am quite well done with today.